We physicists have waited 100 years since 1916 for this photograph of some of the biggest black holes ever recorded in the history of science. Michio Kaku, a renowned theoretical physicist and futurist, has spent decades captivating the public with his insights into the universe's deepest mysteries. In his work, he often discusses black holes, those enigmatic celestial objects that challenge our understanding of physics. Recently, he revealed a groundbreaking development. Scientists have finally begun to unravel what lies inside a black hole. This discovery is not just a monumental moment for the scientific community, but also a profound leap forward in our comprehension of space-time and the fundamental forces that govern our universe. Before we start, hit the like and subscribe buttons for more exclusive news. Black holes have been a subject of fascination for generations. First predicted by Einstein's general theory of relativity, these cosmic phenomena possess such immense gravitational forces that not even light can escape their pull. For years, black holes were theorized as bottomless pits where matter, light, and information disappear, never to return. Their event horizons, the boundary beyond which nothing escapes, have long been the threshold of mystery. Yet what lies inside the event horizon has remained one of the most compelling questions in physics. Michio Kaku's revelation stems from a culmination of recent advancements in both theoretical physics and astronomical observation. For decades, scientists have speculated that the core of a black hole, its singularity, is a point where all known laws of physics break down. The singularity, where the density of matter becomes infinite, has always been the source of both fascination and frustration for physicists. It represents a space where our understanding of time and space ceases to operate in familiar ways. The hope, therefore, was that by understanding what occurs inside a black hole, we might not only solve this mystery, but also unlock new aspects of the universe. One of the major strides forward has been through advancements in technology, particularly through powerful telescopes like the Event Horizon Telescope, EHT. This telescope, using a global network of radio telescopes, managed to capture the first ever image of a black hole's event horizon in 2019. Although that image was only the beginning, it marked a turning point in our ability to study these celestial giants. It offered a glimpse into the mechanics of black holes and paved the way for deeper exploration. However, what Michio Kaku reveals is not just limited to observational advancements. Theoretical breakthroughs have also played a significant role in this discovery. String theory, a major focus of Kaku's own work, offers a framework through which scientists might reconcile the seemingly irreconcilable. Einstein's theory of relativity, which governs the large-scale universe, and quantum mechanics, which governs the subatomic world. At the heart of the black hole lies the singularity, and it is this singularity that bridges the gap between these two theories. Kaku's revelation suggests that inside the black hole, we may finally have the key to a unified theory of everything, a theory that explains both the cosmos and the quantum world in a single harmonious framework. Understanding what lies inside a black hole could also provide answers to long-standing questions about the nature of time. Inside a black hole, time doesn't flow in the way we experience it. According to Einstein, time and space are interconnected, forming what we call space-time. Black holes, with their intense gravitational fields, warp space-time to such an extreme that time may slow down dramatically or even appear to stop altogether at the event horizon. But what happens deeper inside, beyond the event horizon? Kaku and other physicists have suggested that time might not only slow down, but might fundamentally cease to exist in any meaningful sense. This challenges our everyday experiences and forces us to reconsider our most basic assumptions about reality. Another mind-bending implication of understanding black holes is the possibility that they could be gateways to other dimensions or universes. For many years, scientists have theorized that black holes might not just destroy everything they consume, but rather transport it elsewhere. Kaku has spoken extensively about the concept of a multiverse, the idea that our universe is just one of many parallel realities. Black holes, with their incredible gravitational forces and singularities, could provide a mechanism through which matter and energy are funneled into these other universes. If true, this would revolutionize not only our understanding of black holes, but also the very nature of the cosmos. We might find that what lies inside a black hole is not an endpoint, but a portal to an entirely different region of reality. Moreover, understanding black holes could help resolve one of the most perplexing paradoxes in physics, the information paradox. This paradox, first formulated by Stephen Hawking, arises from the apparent conflict between quantum mechanics and general relativity. According to quantum mechanics, information about the physical state of a system cannot be lost. However, when something falls into a black hole, it seems to disappear forever, suggesting that information might be lost. This is in direct conflict with quantum theory. Kaku's insight suggests that resolving this paradox may lie in a deeper understanding of what occurs within the singularity. If black holes do indeed connect to other universes or dimensions, then the information might not be lost. It might simply be transferred elsewhere. The implications of this discovery extend far beyond theoretical physics. If scientists can truly understand the inner workings of black holes, it could have profound effects on the way we think about the universe, the nature of existence, and even the future of humanity. Black holes are the ultimate test of our understanding of nature's laws. If we can unlock their secrets, we could gain unprecedented insights into the birth of the universe, the formation of galaxies, and the ultimate fate of everything. Moreover, black holes could offer clues about the future of space exploration. One of the most tantalizing ideas proposed by physicists is the concept of a wormhole, a tunnel through space-time that could, in theory, allow for faster-than-light travel between distant parts of the universe. While wormholes remain speculative, black holes provide a natural context in which to explore these ideas further. If the structure of space-time inside a black hole can be mapped and understood, it's possible that we could one day harness the power of black holes for interstellar travel. While this remains in the realm of science fiction for now, the growing understanding of black holes brings us closer to realizing these once fanciful dreams. Kaku's revelation also forces us to confront the existential nature of black holes. These objects, which are both destructive and awe-inspiring, serve as a reminder of the fragility of existence. Black holes consume everything in their path, stars, planets, even light. Yet paradoxically, they also play a crucial role in the creation of galaxies and the formation of stars. Without black holes, the universe as we know it might not exist. Understanding what lies inside them, then, is not just about solving a scientific puzzle. It's about understanding the forces that have shaped the cosmos. Furthermore, black holes offer us a glimpse into the ultimate fate of the universe. While we often think of black holes as rare and isolated phenomena, they may actually represent the future of the cosmos. As the universe continues to expand and cool over billions of years, some scientists predict that black holes will become more dominant, eventually consuming all matter. This black hole era, as it is sometimes called, could represent the final stage of the universe's evolution. By studying black holes today, we're not just looking into the depths of space, we're peering into the distant future of everything that exists. In the context of human achievement, Kaku's revelation underscores the power of human curiosity and perseverance. For centuries, black holes existed only in the realm of mathematical theory, dismissed as mere curiosities of Einstein's equations. Yet through the efforts of countless scientists, engineers, and thinkers, we have moved from abstract theory to tangible discovery. Capturing the image of a black hole's event horizon in 2019 was a watershed moment. But understanding what lies inside represents the culmination of centuries of scientific advancement. It's a testament to the human drive to explore the unknown, to ask the big questions, and to seek answers even when the odds seem insurmountable. One of the most tantalizing implications of this discovery is the possibility of bridging the gap between general relativity and quantum mechanics. Black holes represent a region of space-time where these two pillars of modern physics collide. General relativity, developed by Albert Einstein, has successfully described gravity and the behavior of large-scale structures like planets, stars, and galaxies. It paints a coherent picture of how massive objects curve space-time and how that curvature affects the motion of other objects. However, general relativity breaks down under extreme conditions, such as inside a black hole. The singularity at the heart of a black hole represents a point where space-time is infinitely curved, and our understanding of physics as we know it no longer applies. This is where quantum mechanics, which describes the behavior of subatomic particles, comes into play. In the quantum world, gravity appears negligible compared to the other three fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. In contrast to general relativity, quantum mechanics thrives in the realm of the very small, governing how particles interact on scales much smaller than atoms. Yet these two theories are incompatible as they operate under vastly different frameworks. Black holes, with their immense gravitational forces concentrated in a tiny region, present the ultimate challenge for physicists. Understanding what happens inside a black hole could potentially lead to a theory that unifies general relativity and quantum mechanics, a so-called theory of everything. Such a theory would not only explain the behavior of the cosmos, but also the tiniest particles that make up all matter. Kaku's work with string theory, which posits that all particles are actually tiny vibrating strings, offers one potential avenue for this unification. String theory suggests that, at the most fundamental level, the universe is composed of tiny one-dimensional strings that vibrate at different frequencies to create different particles. If string theory proves correct, it could provide the mathematical framework needed to reconcile general relativity and quantum mechanics, with black holes offering a natural laboratory to test these ideas. But while unifying these two theories is a lofty goal, there are other more immediate questions that Kaku's revelation helps address. One such question is how black holes grow and evolve over time. Traditionally, black holes were thought to grow by accreting matter, drawing in gas, dust, and even entire stars that strayed too close to their event horizon. As black holes consume matter, they grow in mass, becoming even more powerful gravitational behemoths. Yet recent research has shown that black holes can also grow through mergers with other black holes. When two black holes collide, they release an enormous amount of energy in the form of gravitational waves, ripples in space-time that can be detected by observatories like LIGO, Laser Interferometer Gravitational Wave Observatory. Moreover, black holes are not merely destructive forces. They play a vital role in shaping the evolution of galaxies and even the formation of stars. At the center of most large galaxies, including our own Milky Way, lies a supermassive black hole. These colossal objects, which can be millions or even billions of times more massive than the Sun, exert a powerful influence on their surroundings. As matter falls into a black hole, it heats up and emits vast amounts of energy in the form of radiation. This radiation can, in turn, affect the formation of stars and the structure of the galaxy itself. By understanding what happens inside black holes, we can gain new insights into how galaxies form and evolve over time. The recent discoveries about black holes, as highlighted by Michio Kaku's revelations, delve deeply into the physical properties and existential questions posed by these cosmic entities. The importance of black holes extends far beyond their gravitational pull and enigmatic characteristics. Black holes have forced physicists, astronomers, and cosmologists to question not only the nature of the universe, but the very foundations of reality. Understanding what lies within a black hole isn't merely a matter of curiosity, it's an exploration that could fundamentally reshape our understanding of the universe itself. One of the most intriguing areas that Kaku has highlighted is the notion of cosmic censorship. This principle suggests that nature conspires to prevent the occurrence of naked singularities, points in space where the laws of physics completely break down and become visible to the universe. Singularities are at the heart of black holes, but they are always hidden behind an event horizon. The event horizon acts as a veil, preventing any information about the singularity from escaping and being observed by the rest of the universe. The cosmic censorship hypothesis, proposed by physicist Roger Penrose, essentially says that the universe protects us from seeing the breakdown of physics that occurs at singularities. However, Kaku's revelations suggest that if we can understand what lies inside a black hole, we might be able to challenge or even disprove this hypothesis. Could it be possible that naked singularities exist? And if so, what would they reveal about the nature of reality? If the veil of the event horizon can be pierced, or if information can escape from the singularity, it would open the door to a realm of physics that we have never before explored. This is no small matter. It challenges the very notion of determinism and causality, cornerstones of modern physics. If information can emerge from a singularity, it suggests that the future could, in some way, affect the past, leading to profound philosophical and scientific consequences. Furthermore, the discovery of what lies inside a black hole has reinvigorated the debate around Hawking radiation. Proposed by Stephen Hawking in 1974, Hawking radiation is a theoretical form of radiation that allows black holes to slowly lose mass and eventually evaporate. According to quantum mechanics, pairs of virtual particles constantly pop into and out of existence in the vacuum of space. When this occurs near the event horizon of a black hole, one particle might fall into the black hole while the other escapes, effectively leading to the emission of radiation from the black hole. This process causes the black hole to lose energy, and over a long enough time period, it could eventually evaporate completely. Hawking's proposal was revolutionary because it showed that black holes were not entirely isolated from the rest of the universe. They could interact with their surroundings through quantum processes. Yet much about Hawking radiation remains theoretical. It has not yet been observed directly, largely because the amount of radiation emitted by a black hole is minuscule unless the black hole is very small. However, understanding the internal structure of black holes, as suggested by Kaku's revelations, could offer new insights into the mechanisms behind Hawking radiation and potentially allow for new ways to observe or detect this elusive phenomenon. The discovery of what lies inside black holes also raises important questions about the fundamental nature of space and time. General relativity tells us that space and time are interconnected, forming a four-dimensional fabric known as spacetime. Massive objects like stars and planets warp spacetime, causing what we perceive as gravity. Black holes, however, warp spacetime to an extreme degree. Inside a black hole, spacetime becomes so curved that all paths lead inward toward the singularity from which there is no escape. But what happens to spacetime inside the event horizon? Does time continue to flow as we experience it, or does it behave differently? Some theoretical physicists have suggested that time might cease to exist inside a black hole. In other words, once something crosses the event horizon, it might no longer experience time in any meaningful way. This is a mind-bending concept that challenges our everyday experiences and forces us to reconsider what time really is. Time, as we experience it, seems to flow inexorably forward from the past to the present and into the future. But inside a black hole, the very structure of space-time is altered, and it's possible that time could behave in ways that are completely foreign to our understanding. If time behaves differently inside a black hole, this could have profound implications for our understanding of the universe as a whole. One possibility is that black holes could serve as natural time machines, allowing matter or information to travel through time in ways that are currently inconceivable. While this remains speculative, it's an area of active research in theoretical physics. Wormholes, hypothetical tunnels through space-time that could allow for faster-than-light travel or even time travel are often associated with black holes in theoretical models. Understanding the internal structure of black holes could provide new insights into whether such wormholes could actually exist, and if so, how they might be traversed. Kaku's revelations about what lies inside black holes also bring up intriguing possibilities about the nature of information and the so-called information paradox. As previously mentioned, the information paradox arises from the apparent conflict between quantum mechanics and general relativity. According to quantum mechanics, information cannot be destroyed. Even when a particle or system changes form, the information about its previous state is preserved. However, when something falls into a black hole, it seems to disappear forever. If black holes eventually evaporate due to Hawking radiation, this raises the troubling possibility that the information about what fell into the black hole is lost forever, in violation of quantum theory. One potential resolution to this paradox lies in the concept of holography, which posits that all the information contained in a three-dimensional region of space can be encoded on a two-dimensional surface. In the context of black holes, this means that all the information about what falls into a black hole could be encoded on the event horizon rather than being lost inside the singularity. This idea, known as the holographic principle, was proposed by physicist Gerard de Hooft and later developed by Leonard Susskind. If correct, the holographic principle could not only resolve the information paradox, but also provide new insights into the nature of reality itself. The holographic principle suggests that the universe we experience as three-dimensional might actually be a projection from a two-dimensional surface. In other words, the entire universe could be a hologram. While this might sound like science fiction, it's a legitimate area of research in theoretical physics. Understanding what lies inside black holes could offer crucial evidence for or against the holographic principle, helping to determine whether our reality is indeed a projection from a higher dimensional space. The revelations about black holes also have significant implications for cosmology, particularly when it comes to understanding the early universe. The conditions inside a black hole are thought to be similar to the conditions that existed in the moments following the Big Bang. Both involve extremely high densities and temperatures, and both represent regions where the known laws of physics break down. By studying what happens inside black holes, scientists could gain new insights into the origins of the universe and the processes that shaped its evolution. Some physicists have even suggested that our universe could have originated from a black hole in a higher dimensional space. This idea, known as the black hole cosmology hypothesis, posits that black holes in higher dimensional universes could give birth to new universes through a process similar to the Big Bang. If this hypothesis is correct, then every black hole in our universe could be the seed of a new universe with its own distinct physical laws and constants. This would suggest that black holes are not merely destructive forces, but also creative ones, capable of giving rise to entire new realities. In addition to their role in the early universe, black holes could also offer clues about the ultimate fate of the universe. One possible scenario for the end of the universe is known as the Big Crunch, in which the universe stops expanding and begins to collapse in on itself, eventually leading to a state of infinite density and temperature, similar to the conditions inside a black hole. Another possibility is the Big Freeze, in which the universe continues to expand, and galaxies, stars, and planets drift farther and farther apart until the universe becomes a cold, dark, and empty place. A third scenario, known as the Big Rip, involves the universe expanding at an ever-increasing rate until the fabric of space-time itself is torn apart. Black holes could play a central role in these cosmic endgames. If the universe is destined for a big crunch, then black holes could serve as the final resting place for all matter and energy, consuming everything in their path as the universe collapses. In the case of the Big Freeze, black holes would continue to exist long after stars have burned out, eventually evaporating through Hawking radiation over the course of trillions of years. In the Big Rip scenario, black holes might be torn apart along with everything else as the expansion of the universe accelerates beyond control. Kaku's revelations about black holes are not only reshaping our understanding of the universe, but also sparking new questions about the nature of reality itself. Black holes, with their extreme conditions and mysterious interiors, offer a unique window into the fundamental workings of the cosmos. By studying what happens inside these enigmatic objects, scientists are uncovering new insights into the nature of space-time, matter, and energy. These discoveries have far-reaching implications, not just for theoretical physics, but also for our understanding of the universe's past, present, and future. One key area of investigation is how entropy operates within the event horizon of a black hole. According to the laws of thermodynamics, black holes possess entropy proportional to the surface area of their event horizon, not the volume inside. This is a surprising and counterintuitive idea because it suggests that all the information about the matter and energy that has fallen into a black hole is somehow encoded on the surface of the event horizon rather than being distributed throughout the interior. This notion aligns with the holographic principle, which proposes that the entire three-dimensional content of a region of space can be described by information stored on a two-dimensional boundary. The study of black holes has therefore forced physicists to rethink the relationship between volume, surface area, and information in the universe. The idea that the entropy of a black hole is related to the area of its event horizon could have profound implications for the study of quantum gravity. Quantum gravity, the long-sought theory that unifies quantum mechanics with general relativity, has remained elusive for decades. Black holes, however, may offer a testing ground for ideas in quantum gravity. By analyzing how entropy behaves in black holes, physicists may be able to develop new mathematical tools to describe spacetime at both the quantum and cosmological scales. This could lead to breakthroughs in our understanding of quantum gravity and the very fabric of spacetime itself. Another fascinating area of inquiry relates to how black holes could help us understand the ultimate limits of information storage and processing in the universe. Black holes, despite their chaotic nature, may represent the most efficient information storage systems in existence. The Bekenstein-Hawking formula, which links the entropy of a black hole to the area of its event horizon, suggests that black holes can store vast amounts of information, far more than any object of comparable size. This raises intriguing possibilities for the future of computing and information theory. Could it be possible to harness the properties of black holes to develop new forms of quantum computers capable of storing and processing information at scales far beyond what is currently possible? Quantum computers, which use the principles of quantum mechanics to process information, have the potential to revolutionize computing. Traditional computers store and process information in bits, which can be either a 0 or a 1. Quantum computers, by contrast, use quantum bits or qubits, which can exist in multiple states simultaneously thanks to the principle of superposition. This allows quantum computers to perform certain types of calculations exponentially faster than classical computers. The study of black holes could provide new insights into the limits of quantum computing, particularly with regard to how information is stored and processed in extreme gravitational environments. The potential implications for black hole research extend even beyond physics and computing, touching on deep philosophical questions about the nature of reality, existence, and consciousness. One speculative idea that has gained traction in recent years is the simulation hypothesis, which proposes that our reality could be a simulated construct created by an advanced civilization. Black holes, with their seemingly paradoxical properties and their ability to warp space-time, raise questions about the nature of reality itself. If the universe is a simulation, could black holes represent glitches or anomalies in the code that underpins our reality? Could the event horizon of a black hole serve as a boundary beyond which the simulated nature of our universe becomes apparent? While these ideas remain speculative, they underscore the profound philosophical implications of black hole research.